Ah, sim, a gente já tá lá no YouTube. Se você for lá no. Eu vou só silenciar nossos microfones, só para ficar a gente por enquanto. Tá faltando um. E aí eu vou. Tem um bannerzinho que a gente coloca aqui um pouco antes de começar, né? Na hora que der 7 horas certinho. Tempo. Boa noite, buenas noches, good evening, everyone. Welcome to our first webinar from a webinar series hosted by the International Association for Hydro Environment Engineering and Research. And we are a Brazil Young Professional Network. We are delighted to have you all here today to explore and discuss the latest advancement in hydro environment engineering field. Throughout this event, esteemed speakers and experts will share the groundbreaking research, fostering valuable discussions and potential collaborations that will shape the futures of hydro environment engineering. So let's engage in fruitful discussions, embrace the spirit of inquiry as we embark on this intellectual journey together. Today, we are glad to receive Diego Casas with his research modeling the transport of outfall sediments under wave action. Diego Casas is a PhD student in the graduate program of Water Resource and Environmental Engineering at Federal University of Paraná, Curitiba, Brazil, where he also completed his master's studies. He's a civil engineer who graduated from Universidad del Norte, Colombia, and worked on consultancy projects in water resource engineer. His research is on the effects of surface of water waves on the transport and fate constituents, especially in coastal and estuarine environments. Topic of interest are ocean outfalls and coupled wave current models for coastal hydrodynamic modeling. Thank you for joining us and let's the event commence. Thank you, Diego. Obrigado. Muitas gracias. Good luck. Tenham uma boa sorte. Podem fazer perguntas em português. Podem hacer perguntas em espanhol. Question can be asked in English at the chat and will be read at the end of presentation. Okay? Thank you so much. That's you, Diego.
Okay, thank you, Fernando. Um, uh, Thank you for the introduction, and I hope this will be a very interesting presentation for all of you, for the audience. And well, today uh, I, I want to present some of my research that is on the effects of water waves on the transport of sediments from ocean outfalls. Okay. Um, First, I'd like to explain what an ocean outfall is. Maybe most of you are not familiar with the term ocean outfalls. We first we need to understand the difference between passive and active mixing. We have the passive mixing, that is the one that occurs as they exist in the environment. So when we discharge an effluent in in an ocean, the ambient currents and turbulence will mix and disperse all of this effluent. However, if our discharge has a very high velocity or linear momentum, it will generate uh, a flow field that will enhance dilution. This is what we call active uh, mixing. An outfall system, it makes use of the active mixing principle, and it is frequently coupled with some kind of treatment. It can be a preliminary treatment or a primary treatment. So we can reach dilutions of up to 100 or even 1,000 higher than a passive mixing. Here we have a very simple scheme. Uh, the domestic or industrial effluent, it goes to a wastewater treatment plant. Okay, it receives a preliminary or primary treatment, and then it is pumped into the outfall, and at the end, it has a a diffuser that has several orifices. These these orifices enhance the dilution. So when our effluent is discharged in our water body, in this case, the ocean, a coastal region, we have a high velocity here, a lot of turbulence, and an enhanced dilution associated to it. When we analyzed a submarine outfall, we usually divide the the regions into three parts. We have a near field that it has a jet-like behavior in which the velocity and momentum is higher. Then we have a plume-like region that it's called the far field, in which the effluent is transported passively by ambient currents. Okay, and about ocean outfalls, we have some survey of 2011 by the Institute of Hydrodynamics of the Karlsruhe University in Germany. It reported about 200 outfalls worldwide, most of them in countries like Venezuela, Spain, United States, United Kingdom, Puerto Rico, and in Brazil, it reported about 14 outfalls. However, we currently have about 20 outfalls in Brazil. Most of them are located in São Paulo state, about 9 of them. Okay, and in this presentation, we will focus on this far field that I mentioned. Okay, because the ultimate fate and long-term transport depends on the far field. Here, for example, we have the far field plume can be modeled using 2D or 3D hydrodynamic models that they usually solve the Navier-Stokes equations. Some examples of these models are Mike 21 or Mike 3. We have RUMS, that is an oceanic circulation model. We have MOHIT and DEL3D. We can consider several forcings in our models. For example, tides, astronomical tides. If our region is influenced by river discharges, we can consider them too. Sometimes wind can have significant impacts, so we can consider surface wind as one of our forcings. Also, temperature and salinity, they can have a significant impact in water quality if we're coupling our hydrodynamic model with a water quality model that usually solves the advection diffusion equations. Also, we can consider heat and freshwater fluxes that they can have an impact on temperature and salinity, and in turn in our water quality. However, there are still some processes that have not been properly investigated or not well understood. One of these processes is wave motion. Several authors since the 90s have been pointing out that waves, they can play a significant role in the resuspension of outfall sediments. And interestingly, including waves in the far field outfall models is not common in the current practice. Several field observations have shown or have suggested that wave motion can resuspend or prevent the sediment deposition, and it can in turn have impacts on the local benthic system. And more recent modeling studies have suggested future work on the consideration of the solid particles in the effluents and the potential pollutants that can attach to these solid particles, and also the interaction of waves with these solid particles. In summary, we have the interaction between sediments and waves. We have that waves, they can resuspend sediment, and this sediment reentrainment, it can act as a pollution input, as a pollution source to our overlaying water column. We, on the other hand, have the outfall effluents. They can produce sediment pollution. They can increase the concentration of trace air metals, of toxic organic contaminants on in our sediments. Um, we propose a case study in order to understand the effects of waves on the transport and fate of sediments from outfalls. This case study consists of 5 submarine outfalls in Baixada Santista. Baixada Santista is a metropolitan area in the coastal central region of São Paulo state in Brazil. Um, those those 5 outfalls are operated by the sanitation company of São Paulo state, Sabesp, and the case study is data for 2019. We have our 5 outfalls, all of them with lengths between 3 and 4.5 kilometers. All of them are in relatively shallow waters, between 11 and 14 meters. And 4 of them have mean discharges below 1 cubic meters per second. Only the one in Santos that is here and discharges in the middle of the Santos Bay has a discharge of about 2 cubic meters per second. Several studies have been done on these outfalls, especially on the Santos outfalls. And a study in 2021, it considers sediment deposition in the model, and it found that the model reproduced a deposition of about 25 centimeters per year in the middle of the Santos Bay, which we found to be unrealistic since a sediment deposition of this magnitude have not been observed in the field. So we suspect that there is a forcing or some kind of phenomenon that prevents this magnitude of sediment deposition. We also have a previous study of 2017. It was testing several length extensions for the Santos outfall. And it found that the longer the outfall, the less the sediment deposition. And it makes sense since the longer outfall extensions, the diffuser and the plume is exposed to stronger offshore currents, which just they transport this sediment seaward. We propose a hydrodynamic model. The model was set up using the flow module, the hydrodynamic module of the Del3D modeling suite. The model is depth averaged, so it is 2D, two-dimensional. We used 2 independent periods for calibration and validation for year 2012. And the actual study, as I already mentioned, was performed for 2019, in which we have data for suspended solid for sediment in the effluents. For both years, for 2012 and 2019, we considered several forcings such as astronomical tides, salinity, temperature, wind, heat flux along the water surface, also Coriolis forces. We considered freshwater discharges for several rivers and channels along the coast, and of course the outfall discharges. Then for 2019, we considered suspended solids in the outfall discharges. Our simulation grid, it had about 75 kilometers in the longshore direction, and it extended about 28 kilometers seaward. It is a curvilinear grid with a variable resolution between 36 meters in the regions near the coast, and it had a coarser resolution of about 1 kilometer in the deeper regions. Then for the sediment transport, based some granulometric studies, we divided the sediment in two fractions, for cohesive sediment and the other one for non-cohesive, sandy sediment. As you can see here in the granulometric curve, about 82% of it is cohesive and about 18% is sandy sediment, non-cohesive sediment. We also consider some studies on the sediment composition, and we found that about 80% of it is volatile type sediment that is usually associated with organic rich sediment, which has lower density than mineral or fixed sediment. That's why we applied a correction to the sediment density, and it went from about 2,600 to 1,500 kilograms per cubic meter. Then the sediment concentration of the effluents was estimated based on operational data by Sabesp. We have that the Santos outfall has about double of the sediment concentration in the outfalls of Guarujá and Praia Grande that are outside the Santos Bay. And for our wave model, we use the wave module that is based on the SWAN wave model. This uses a spectral description of waves in which we don't consider regular waves. We consider that a wave state or a sea state is a combination of several linear waves, several trains of regular waves. We use data from a wave buoy in the middle of the Santos Bay for 2016 in order to validate our model. And for the actual study, we use a wave current coupling with the hydrodynamic model for 2019. So for both periods, for the validation period and for the actual study for 2019, we used energy input by wind. We also considered nonlinear wave-wave interactions. We considered some energy losses by bottom friction, depth-induced breaking, and white capping. And our modeling grid, as you can see, is larger than our hydrodynamic grid, that is the one with this gray dashed line, because we wanted to propagate wave condition from deep waters into the coast and the Santos Bay. Our wave grid had about 100 kilometers longshore, and it extended 42 kilometers seaward. The resolution for this grid was fixed of 200 meters. Then we selected 3 months with representative wave conditions for 2019. January was found to be representative of mild wave conditions, while July was found to be representative of strong wave conditions. And March had mean wave conditions with respect to the whole year of significant wave heights in the region. Then we proceeded to calibrate and validate the hydrodynamic and wave model. For calibration, we use data from a tide gauge. So we use water level data at a station here in Praticagem Santos. It is inside one of the channels that discharge into the Santos Bay. We achieved calibration up to a Wilmot index of performance of 71%. And then we validated with data from a different period and a different location. In this case, here in Ilha das Palmas. It's a small island here in Santos Bay. And we achieved the validation with a Wilmot index of 72%. with respect to the wave model, we use data from this buoy here in the middle of Santos Bay, and we found a Wilmot index of 78% for the wave height. The wave period series measurements weren't as clean as the wave height series, so we found significant deviations here. However, since the wave suspension depends on the orbital wave motion and it is directly proportional to the wave height, we consider that the model was appropriate for our simulation. Then some of our results, we have, for example, the total suspended sediment. We found that without waves in all of the months, January, March, and July, that correspond to mild, mean, and strong wave conditions, we found that the sediment plume that was suspended in the overlying water column, it was more or less concentrated in a radius of about 1 to 2 kilometers. Okay. However, when we consider waves, that would be the second column here, especially for mean and strong wave conditions, we have the plumes becomes larger and larger. And a very interesting behavior is that these plumes, they're advected, they're transported by currents that are longshore. So this suspended sediment is mobilized westward. Then we can compare the sediment concentration, the order of magnitude of the sediment concentration. We found, for example, that the effluent concentrations are all in the order of 10 to the minus 1 kilograms per cubic meter. And after release, it goes rapidly to a concentration of about 10 to the minus 3 or even lower. However, if we compare these concentrations with the natural sediment concentration in the bay, as they were found by Berzin in 1992, the ambient sediment concentrations are in the order of 10 to the minus 2. So these concentrations of sediment from the outfall, it rapidly goes below the ambient concentrations. Now, if we compare the different fractions, the cohesive and non-cohesive fraction, first for the cohesive fraction, we found that the presence of waves greatly affects the suspended sediment concentration. This is for mean wave conditions for March of 2019. And also for the bed sediment mass, this is the bed sediment deposit. We can see that the bed deposits have more or less the same shape as the plume. And for the non-cohesive sediment, we can see since it is only about 20% of the total sediment. In the case of the suspended sediment concentration without waves, we see almost none of it. However, when we include the effect of waves, then it becomes dispersed along the coast. For the bed sediment mass, we can see here that the non-cohesive sediment is concentrated in a small region around the outfall diffusers. And when we include the waves, this sediment is resuspended and it becomes dispersed along the coast and inside the Santos Bay. Then for the total sediment deposition, we converted the previous quantity, this was kilograms per square meter, to a bed sediment layer thickness using the bed sediment density. And we again see that the inclusion of waves here in the second column, it produces a more dispersed sediment deposit at the bed. And we can see again this sediment that is advected by the currents, by the longshore currents. It settles far from the discharge location, and it can even reach the channels. Like for example, this one here, the Santos channel and the Bertioga channel at the left, or it can even reach the some of the nearby coasts near outfalls, for example, PG1, PG2, and PG3. If we analyze the sediment thickness, the sediment bed thickness near the diffuser, near the discharge location, we can see for January that has mild wave conditions, that there are some sediment resuspension events around day 5, day 10, and day 20. We have for Santos, for example, that considering waves, this would be the red line. We have the final sediment thickness is about 55% lower. And for an outfall like PG3 that has the lower discharge, and we found a reduction of about 44% in this sediment layer thickness at the bed. However, for July, that has the strongest waves, this reduction of the sediment bed deposit can be significant. We're talking about 90% in the case of Santos. So in about a month, it goes from a sediment thickness of 1.5 centimeter to just a couple of millimeters. For the case of PG3, it has a reduction of 83%. So we can see that our line here in black, it reproduces a linear deposition, almost unperturbed. The inclusion of waves produces that our deposition is not unperturbed. It has some frequent events of resuspension that avoids this unrealistic deposition at the bed. If we compute the deposition rate, in this case only for Santos, we see that the undisturbed deposition, I mean without waves, is about 0.06 centimeters per day, which in about a year is a deposition of 20 centimeters. It is considered unrealistic since in a span of several years, we would have about a meter of sediment deposition, and it hasn't been observed in the region. Then the waves, they resuspend this sediment and reduce the rate of deposition. As we can see, for example, for March here in the middle panel, here the line in red is the deposition rate with waves. We can see that it's lower. And when it crosses this gray line, it goes to negative. It becomes a resuspension. The same for July, in which we have resuspension events too, and the deposition is lower than the black line. That would mean an undisturbed deposition without waves. If we analyze further the deposition rate, in this case for March, that has mean waves, we could compare it with the depth average velocity of the current, and we can see that there are not significant differences between the velocity without waves and with waves. Okay. However, if we compare our deposition rate against the the near bottom wave orbital velocity, there are some peaks that they coincide with these events of sediment resuspension. When you have these peaks in the orbital wave velocity, we also have events here of negative deposition rate. This can be explained using the Soulsby theory. That it says that the oscillatory stress in a wave current environment that has two components, a time mean component and a maximum component. And it is composed of a current alone stress and a wave alone stress. And this oscillation is induced by the wave alone stress. We can study the wave regime for Santos, for example. We know from linear wave theory that the depth wavelength radio is an indicator of the wave regime. In this case, the lower limit of wave action is found at the depth wavelength radio of about 0.5. If we plot this depth wavelength radio for Santos for the three periods, January, March, and July, and we also plot this 0.5 line, we can see that there are some incursions of this curve, of this black curve, below the lower limit of wave action. When this black line goes below the red line, well, we have some transition of a deep water regime to an intermediate water regime. In this intermediate water regime, it would be something when the wave orbital motion, it becomes affected by the bed, as you can see in this graph here. Okay, the below this lower limit of wave action, we have no perceptible motion of waves. Once the waves start to interact with the bed, those bed stresses, those wave-induced waves stresses, they start to resuspend sediment, they steer up the sediment. For Mars, that has mean wave conditions, we can see that most of the time the black line is below our lower limit. So most of the time it is preventing the deposition and producing resuspension. And for July, we have very similar conditions in which most of the time this black line is below our limit. So we have again a reduced deposition and frequent resuspension events. We can further study our near bed orbital velocity using linear wave theory. I already mentioned that this orbital velocity is directly proportional to the wave height. And if we compare the near bottom wave orbital velocity against the significant wave height, we can see that the time series are very similar. We can see that there are some discrepancies. Those are induced by the period and the wave number k, but it mostly resembles the wave height. So that's why I said that the wave height has the most significant role in the orbital velocity and those wave-induced bed stresses that resuspend and steer up bed sediment. We can draw some conclusions from our study. One is that the consideration of waves, it can avoid unrealistic sediment deposition in the long term, because we found that disregarding waves, it produces sediment deposition in our model of about 20 centimeters per year. The inclusion of waves avoids this unrealistic sediment deposition. We also found that the resuspended sediment, it can be transported further. It can even reach the coastline and nearby channels. And as future work, we can say that using coupled with current models for the outfall plume modeling, it allows us to understand the fate of sediment-attached contaminants. I hope for the future people to couple this kind of wave current models with water quality and sediment quality models to understand what happens with those pollutants that are attached to the sediment particles. And we could also identify areas of potential environmental concern. So the principal recommendation here is for future studies of outfalls to consider potential effects of waves on the design and operational conditions. If some of you are interested sharing some ideas on outfalls, here is my email. I also have a website, and I would like to acknowledge CAPES and SABESP, in this case CAPES, for providing some financing for the research, and SABESP for providing most of the data for the models. Thank you very much. And if you have any questions, as Fernando already said, you're welcome to write them in the chat.
Thank you so much, Diego. I think that's a great opportunity for discussion and great presentation. We have, in fact, two questions here in the chat. The first one is Caio. Thank you, Caio, for your question. He asked about, have you used a neural network for creating this model?
We haven't tried using neural network. However, I have a colleague that is trying to implement some big data into this kind of model to study water quality.
Okay. The question, Victor Hugo. Thank you, Victor. Hi, thank you for a great talk. How are uncertainty handled in 3D modeling?
Well, with respect to uncertainties, there always will be uncertainties. We try to minimize them by doing the calibration and rigorous validation of the models. However, there are some variables that are outside our control, and we do lots of sensitivity analysis in order to estimate the effect of those variables. In this case, for example, the dimensionality of the model, because we tried to run 3D models and the 2D model, and we found that there were no significant differences between the 2D and the 3D model in this case. And it was justified by the fact that the Santos Bay and the outer coastal region, it is well mixed. The water column is well mixed most of the year. So that kind of analysis we perform to minimize uncertainties.
We have another one. And another question is, Victor Hugo, can you go over again what are the computational costs in running the simulations?
Computational cost. The hydrodynamic model, it spent about 45 minutes to run a single month. Okay. However, the wave model is quite expensive. For it to run a single month, it takes around 21 hours. So when we're running coupled simulation of waves with hydrodynamics, we're talking about a single day in order to run a whole month.
We have a commentary here, Claudio Oliveira. Great work, great presentation as well. Thank you.
Thank you.
Claudio. And myself, I have one question for you, Diego. I'm not expertise, but I have one curiosity, in fact. what about the effects of some hydraulic structures, such as, for instance, example, jets? In Portuguese, is quebra-mar. How to consider that in modeling?
Well, there is a possibility of including that kind of structures in the 3D. You input them as linear structures. What the model do is it implements an obstacle in the flow. So it could be a completely impervious structure that it doesn't allow for flow to pass through, or it can let some of the flow or even the waves to pass through the obstacle. It is completely possible to do it on the 3D.
Okay. So I don't think that we have another question. So again, thank you, Diego. Thank you for everyone who watched your presentation. The first one of our
Many.
web series of many, of course. We are the Young Professional Network from International Association for Hydro Environment Research. So, good evening, everyone. Good evening, Diego. Thank you again. Muchas gracias. Obrigado.
Good evening, everyone, and thank you, thank you for the questions. Thank you to the audience for the interest, and see you next month in our next webinar.
Yeah. Thank you, Rafael Rodriguez. Also, he's made a commentary. Very good presentation, Diego. Thanks to Young Professional Network Brazil for organizing the event. Thank you, Rafael.
Thank you, Rafael.
Bye, everyone.